All right, 9.1 starts talking about probabilities. This is one of my favorite sections. I find probabilities to be sort of interesting to work with. And so we're going to take a look at some different things that have probabilities. So to start with, we're going to talk about an experiment. An experiment doesn't have to be like in science. That's where you hear the word probably used the most. But an experiment, as we're going to talk about it, is any activity where you can observe and record the results. So if you were to take a coin and you were to flip it 50 times, that would be an experiment. And you wrote down what the outcome was every time. Okay? If you took a dice and you rolled it 100 times, that would be an experiment. Okay? If you looked at a sample of people and you counted how many boys versus girls they had, that would be an experiment. An outcome is just the possible results of an experiment. So if you were flipping the coin up and down, the possible results would be heads and tails. That's it, right? If you're rolling the die, the possible results would be 1, 2, 3, 4, 5, or 6. Okay, if you had a standard die. If you were looking at the boys and girls, the possible response would be either boy or girl. Or if you were counting them, it might be a number, right? If you're having the number of boys or numbers of girls, you might have numbers instead of that. Now, a sample space takes the outcomes and it includes all of them in a list. So let me give an example. I haven't written any of these down yet, but let's say, for instance, we did the coin toss here. So our possible outcomes are heads or tails, and then the sample space would look like something like this if we were to abbreviate. So you list them in curly braces, and you write any outcome that's possible right there from a single part of your experiment. In my case, that was a single coin flip. And then an event is any subset of the sample space. Now, that doesn't end up being very interesting on this problem because there are only two possibilities, right? You have heads or tails. I mean, there aren't any different things. But imagine that you did the dice. You rolled the dice. Well, you might have an event that's rolling an even, or an event that's rolling an odd. Or some games, when you play them, right, have some kind of a thing where if you roll a 1 or a 2, certain events happen, certain things happen with that. So an event is just some smaller collection of what's going on in the whole sample space. Theorem 9.1 is called the theorem or the law of large numbers. It's Bernoulli's theorem. And what it says is that if you have an experiment and you repeat it a large number of times, then the probability reaches a fixed number. So imagine rolling, or we'll just do our same thing with our coin toss. Imagine tossing the coin, right? So you may get 6 heads in a row. Agreed? I mean, this is possibility. This is what happens when people have, lots of children and they have 6 girls in a row. You know what I'm talking about, right? But over the span of everybody having children, it should all even out to be about 50-50, right? That's what it should do. That's Bernoulli's law of large numbers. He's saying that if I flipped that coin a large number of times, I should get pretty much the same number of heads as I do tails. Does that make sense? Okay, that's all Bernoulli is saying. If you take a look at a probability, the probability is calculated as the number of ways that you get your event to happen, whatever event you're trying to get to happen, divided by the number of ways that you get your sample, or the number of items that are in your sample space. So this N before it means number of something happening. Okay? So for instance, if you talked about a coin toss, or not a coin toss, let's do a dice roll. If you talked about rolling a dice, how many ways can you get an odd number? 3 ways to get an odd number on a standard 6-sided die, right? How many different things could you get, generally speaking, on that die? 6. So the probability of rolling an odd would be 3 over 6, and then of course we would reduce. So probability is just the number of ways of getting whatever event you want to happen, divided the number of ways that anything could have happened in your situation. Mutually exclusive, and we will encounter, I think it's on the next slide, no, it's later on, we will encounter something called independent. Mutually exclusive events are events that have no elements in common. So the notation that we use is something like this, and I will explain. This is notation some of you have seen before. We encounter this notation in elementary math 1. A and B are different events. This here is the symbol for the idea of the word and. It's the intersection specifically. And this right here is called the null set, or you could say the empty set. All mutually exclusive events are events that can't happen at the same time. For example, rolling an even and rolling an odd. Can't happen at the same time. You don't have something in both of those categories simultaneously working. All right? If you want to think about streets, Harrison and Kickapoo never cross. Right? They never have anything in common. You cannot be on both Harrison and Kickapoo at the same time. Agreed? Can't. Okay? So you could give lots of examples where things don't intersect. All right? We're going to take a look then at Theorem 9.2. Theorem 9.2 says that if you have an event A and you have a sample space S, then the probability of your event, any event, has to be between 0 and 1. Now that should make sense because 0 means it never happens, right? Obviously, that's a possibility. It is never going to happen that I'm going to do certain things. I'm never going to skydive. Never going to happen. 0% chance. 0 probability. 1 is a for sure thing. It absolutely will for sure and always happen. Okay? So if you were rolling a die, for instance, and you said, what's the probability that you get a number 1 through 6? 100%, right? Like it's going to happen because it can't sort of land on its edge or like, you know, I guess it could disappear down a storm drain or something, I don't know, but it's going to for sure land on something, right? So the maximum, the highest value is going to be 1, 100% chance. The lowest value is going to be a 0. So whatever probabilities that you're looking at have to fall between 0 and 1. Some percentage chance between the two. Theorem 9.3 says that the probability of an event is equal to the sum of the probabilities of disjoint outcomes making up the event. So we're going to consider rolling a 6-sided die, and let me give you some events. Let's say that the event A is that you roll an even number. And event B is that you roll, let's do a 3. Okay, there's 2 different events. They are disjoint, right? They can't happen at the same time. We could also say they're mutually exclusive. You can't roll an even and roll a 3 at the same time. So there are 2 ways of calculating this probability. One way is to figure out what is the probability of event A and what is the probability of event B, and you can add them together. And that's what this theorem is saying. So what is the probability that you roll an even number? Don't reduce for me. 3 over 6. What is the probability that you roll a 3? 1 over 6. And if we add those together, we get 4 over 6. And that's exactly what we would have done if we simply counted the number of ways all of that could happen, right? All the evens and the number 3, and we'd written it over the number 6. Okay? That's all Theorem 9.3 is saying. Okay, so all of this is down here. Theorem 9.4 says that if you have events A and B and they are mutually exclusive, then the probability of A union B is the probability of A plus the probability of B. And that's actually an application of Theorem 9.3 because mutually exclusive and disjoint mean the same thing. The way I figured out how many ways or what's the probability of rolling an even number or rolling a 3 is that I counted the number of ways of rolling an even number, I counted the ways of rolling a 3, I added them together, and I divided by the number of outcomes in the sample space, right? Yeah, I mean, this works. But it's hinged on it being mutually exclusive. Now, you might look at that and say, I don't know what else options there are. Well, what if instead I said the probability of rolling an even for A, and B, I said the probability of rolling a number bigger than 3. You guys tracking with me? The even numbers are 2, 4, and 6. Rolling a number bigger than 3 is 4, 5, and 6. But that's not 6 ways, right? There's things in both of these sets, so I can't just simply say 3 plus 3 is 6, 6 over 6. It doesn't work. because there were things that were in both of those descriptions, namely 4 and 6, right? So I would have to actually somehow exclude the things that I double counted, the things I counted twice. So if you have an event A, we'll talk more about Theorem 9.4 here in just a second in a broader sense. But Theorem 9.5 says that if you have an event A, then the probability of event A plus the probability of the complement of event A, and again, I'll talk a little bit more about this notation, equals 1. And there are several varieties of this formula. So we could also write this formula as the probability of event A is 1 minus the probability of A complement, or the probability of A complement is 1 minus the probability of A. This is just moving pieces of a formula around. That's all it is. So let me tell you what A complement is for those of you who haven't seen this notation before. This is everything not in A. So if you wanted to think about our even example, this would be, the complement of rolling an even would be rolling an odd. Everything that's not in the case you looked at. The complement of having a number bigger than 3 would be having a number less than or equal to 3. It's the things that we're excluding from the description. So the two probabilities added together would have to equal 1 because I've included everything in one set or the other when I've described it. So that's what's happening there. Now there are 6 probability theorems. We'll write these down and then we'll stop for today. We've already mentioned most of these, but I'm going to write them in notation now. The first one says the probability of the empty set is 0. All that's saying is the probability of something that cannot happen would have the probability of 0. Absolute 0 probability it's snowing outside today. Agreed? It can't happen. It's too hot. It's not possible. Okay? So this is a 0 probability. This is what we would call an impossible event. Now, make no mistake, we all recognize, or at least I hope we do, that God can overrule impossible events. So I'm talking about from a mathematical perspective. It's not going to snow today. So don't you go see it snow today and then tell me that I was wrong mathematically. It could, but not in Oklahoma. Good point. All right, so here's another one. We've got the probability of S. S is the sample space, remember. This is 1. And this was my example where I said, let's just say probability that I roll a number 1 through 6. Well, yeah, those are my choices, right? It's for sure. So this is called a certain event. This is why I laugh when it's raining outside and I look at my phone and it says chance of rain, 40%. And I think, really? Looks like 100% to me. Like, it's happening right now. Right? All right. The other one, we've already actually seen this one specifically written, is that if you have any other probability, it has to lie between 0 and 1. It could actually equal one of those, but it can't be something bigger than 1 or smaller than 0. That doesn't work. And that's why it's funny when you guys hear somebody say something like, I'm 110% sure. You're like, they don't really mean that mathematically. They're sort of making an emphasis of something. But mathematically, you can't be 110% sure. Right? 100% sure means you are absolutely certain. There's no way to get more than 100%. So this is for any event A. All right, number 4 we saw written above on the last page of theorems. Let me say it that way first. If the A intersect B is the empty set, that means they're mutually exclusive. Then the probability of A union B, that means the probability that either one of those happens, is the probability of A plus the probability of B. We already saw that one written down. And this, of course, is for events A and B that are mutually exclusive. Now let's talk about what happens in general, though. Because I gave you an example where I said, that's great if they are mutually exclusive, but if I looked at the even numbers and I looked at the numbers bigger than 3, those aren't mutually exclusive, so what then? Because obviously that doesn't work. Well, so if I have events A and B that have any other probability, I don't think I need the word if there, sorry. So the probability of A union B in general is the probability of A plus the probability of B minus the probability of A intersect B. And those of you who are in Math 1 right now, Carrie Ann and Kenna, you guys have seen this like in the last few days. Those of you who've taken Math 1 before have also seen this, but it may have been a little while ago. Those of you who haven't may not have seen this notation before, so let me explain just a little bit. Union simply means that any of those things happen. A happens or B happens. Intersection, that last piece right here, means they happen at the same time. So what this is literally saying is that if I gave you my example of the evens and the numbers bigger than 3, we could count the even numbers, we could count the numbers bigger than 3, and then we could remove however many I double counted. That's this part of minusing at the end. So I counted 3 items that were bigger than 3, I counted 3 items that were evens, and there were exactly 2 items I double counted, so I'd have to subtract 2 off of my counting. That's why I would end up with the 3 in one set and 1 more from the additional set for a total of 4 items in my description. Okay, so this is just removing double counts. And this works for any events A and B. It actually works if it's also mutually exclusive, because if it's mutually exclusive, what's the probability of them happening at the same time? 0, right? If I have probability of the evens, probability of the odds, they cannot happen at the same time. That's a probability of 0. Can't happen. And the last one we've also seen written down. It says, it's one version of it anyway, the probability of the complement of event, that is the probability of an event not happening, is 1 minus the probability of event A. So the next time you're looking gloomy and you're saying, oh my goodness, it's a 40% chance of rain, it's a 40% chance of rain, how about instead you say it's a 60% chance of sunshine? That's what that means, right? It actually does. That's all this is saying. This is saying that if you take a look at that, you can define that in the opposite way as well.